All right, ladies and gentlemen, in meteorology, this is a quick demo to help you with two basic concepts: relative humidity and dew point temperature. So this was shared with me by Mike Thompson from Channel 4 News. This is how he said he would describe relative humidity and dew point temperature to students that were trying to figure out why we choose percentages to represent how much moisture is in the air. I've got 5 beakers here. Each beaker has a temperature on it ranging from about 10 degrees Fahrenheit all the way up to 95 degrees Fahrenheit. The pattern is that the higher the temperature in the air represents a larger capacity for water vapor to be in the air, okay? So in other words, on a 95 degree day, the amount of water vapor that could be contained, the amount of moisture in the air, is much greater than the amount of water vapor that the air can contain when we have a 10 degree or very, very cold day, below freezing, right? These temperatures are all meant to be in Fahrenheit, by the way. So here, let's start off with relative humidity first. If we are at an air temperature of 40 degrees Fahrenheit, I've put water in this beaker to represent not liquid water in the atmosphere, but water vapor in gas form. So keep that in mind. We're using a beaker to represent the air, and we're using this water in the beaker to represent the moisture that could be contained in that air. So I've filled it up about 50%. It's meant to be halfway. If the air, by definition, is holding 50% or half of the moisture it could hold before it becomes saturated or totally full, we would call that 50% relative humidity, okay? 50% relative humidity just means at that temperature, in those conditions, the air contains about 50% of the moisture that it could normally hold, all right? Now don't worry today about how the moisture got there or how to change the amount of moisture in the air. We're gonna keep this water, the amount of water or water vapor, constant the whole time. Watch what happens when the air begins to warm up. If the temperature outside goes to 70 degrees, but the moisture in the air stays the same, then what happens is the air at 70 degrees has a greater capacity. It can hold more moisture, right? But this beaker is clearly not 50% full. It's the same amount of water vapor as before. The only thing that's happened is the air is warmed up, and now we're at something maybe around 15%, 20% relative humidity, but it's the same amount of moisture. What if the air continues to warm? If the air jumps up to 95 degrees, the capacity of that air to hold moisture greatly increases. But if we have the same amount of water vapor, look at this. This is probably down somewhere around maybe 10% relative humidity, maybe 12 or 13, right? So as the air warms up, what normally happens is relative humidity drops, because that's what we chose to use in the United States. It's a percentage of how much moisture is in the air compared to how much it could actually hold. The only way to get to 100% relative humidity is to have the air at that temperature absolutely brimming or completely saturated with moisture. All right, let's take it the other direction. At the end of the day, the sun goes down and the air starts to cool. Well, as the temperature drops, the capacity of that air to hold water drops as well. So when the temperature goes down, the relative humidity goes up. Look how full this beaker is, back to about 50%. Now watch what happens if the air gets cold enough. If it cools off and its capacity to hold moisture drops enough, then this amount of moisture, sooner or later, oh, I've made a mess, right? It fills or is at capacity. This is what we would consider to be 100% relative humidity. The air cannot hold any more moisture at all, right? Now there's a misconception. I get students all the time that say, oh, that's when it rains, right? And no, that's not the case. This is when dew begins to form on trees and on benches and on grass, right? On your shoes if you're sleeping outside, or a tent if you're camping. The temperature when the air becomes completely saturated is when that dew starts to form. Now the tricky part about this is the dew point temperature is not always the same. It totally depends on how much moisture we actually start off with, right? If we get rid of some of this water, just forget that it's there, right? If the amount of moisture in the air, even at this low temperature, is still not at capacity, then even at a temperature of 20 degrees, we will not get the formation of frost or at a warmer temperature, we won't get the formation of dew, right? The dew point temperature changes every day depending on what the temperature is outside and how much moisture there is in the air, okay? One last idea to let your brain work through. If we hit 100% relative humidity, the temperature that we are at in that moment, if it is above freezing, if it's above 32 degrees Fahrenheit, then dew will start to form, okay? It will condense on the grass and on the cars and on homes, right? But if the dew point temperature, if we get 100% relative humidity at a temperature that is below freezing, then we don't get liquid dew that forms, we get frost that begins to form. And that's what we call deposition. The change from water vapor in the air, which is gas, directly to a solid is called deposition. So we'll practice more with dew point temperature in a few activities and demos on another class day. Hope that made sense. If not, let me know.